going to use complete the square, the coefficient of x squared should be positive. So that's what I did here. So what I did here, I just took, minus 1 out. You factor out, in fact, 1, minus 1. And be careful, the minus 1 here cannot be taken out of the square root. The reason is the square root of minus 1 is undefined. I'm going to leave it just inside like that. And I'm going to, complete this square. And as I told you last week, when you want to complete the square, you identify A and B, and you find the missing part. So here A is 1 because the coefficient of x squared is 1. So that's why the coefficient of x squared is A squared. So when A squared equals 1, A equals 1. And so if A is 1, this should squared times x u squared. Okay? Just want to write it again because it's not clear. It's the b squared. Okay? All right, so here x squared, and we have b u squared. And we have the same situation here. This is my a square. All this, it means a equal to 6. And all this bracket is my capital X. All this is my capital X u squared. And b is equal to 1 here. And that's what I told you. Anytime you complete the square, so you will get either the summation of 2 square or the difference of 2 square. So here we have the difference of 2 square. 36 is the square of 6. And this is a square, is my capital X square. And from this, I told you your X is gonna be, based on what we did last week, is gonna be A over B sine of theta. Okay? In my example here, as I told you, A equal to 6, B is 1, and my X here, the capital X, is all these brackets. So it means I have to use this substitution. And that's what I did here. All this is my capital X equal to A over B sine of theta. And you calculate your dx. So when you calculate dx here, we're going to be just dx, and this is a constant, the derivative is going to be 0. So you differentiate your right hand side, you'll get 6 times the derivative of sine, which is equal to cosine theta d theta. And now we're ready to substitute. Okay, so we substitute here x by its value just by using what we did at the beginning. I'm not using this, but what I'm substituting is, I'm gonna erase this. Now from our substitution formula, I'm gonna substitute here. You substitute x because this term is exactly this one. We've seen in the previous page how to go from this step to this one. You substitute x by, because you guys can see from here what is x. So from here, x is going to be 6 sine theta plus 3. You move this -3 from left to right. It becomes a plus 3. So that is my numerator x. All this obtained from the substitution formula. And the denominator here will get 36. That's this 36 here. And you substitute x minus 3 by its value. Here, x minus 3 equal to 6 sine of theta. And you square it. That's why we got here 36 sine square theta. Okay? And the dx, here I replace it by its value, which is equal to 6 cosine of theta d theta. That's exactly what you have in the right here. Okay? Now, under the square root, I have 36 as a common factor. I'm going to take it out. It becomes only 6. And the square root becomes 1 minus sine square because the 36 is already out. And root of 1 minus sine squared, you guys know 1 minus sine squared is equal to cosine squared. And you will get here square root of cosine squared. That's why it becomes a cosine. And 6 cosine is simplify here. The 6 cosine, this one. And the integral becomes a 6 sine of theta plus 3 d theta. So quite easy to integrate it. So the integral of sine theta, as you know, is minus cosine theta. You multiply by 6. And the antiderivative of 3 going to be 3 theta plus the constant c. Now, we have to substitute back. As I told you, anytime guys use a substitution rule or trick substitution, in both situations is just substitution. You have to substitute back in order to express your solution in terms of x. And to substitute back, we're going to use this substitution here. And this is obtained from the right triangle here. You guys can see from this substitution formula, sine of theta is equal to x minus 3 over 6. So it means x minus 3 is the opposite side and 6 is the hypotenuse, and that's exactly what I represent here. This is the opposite side, x minus 3, and this is, the hypotenuse equal to 6. In this case, the adjacent side gonna be just by using, Pythagorean theorems, gonna be just the square of 6 minus the square of the opposite side. And from there, you guys calculate cosine. It's obtained from the right triangle. Cosine is equal to adjacent side over the hypotenuse. So here I substitute, cosine of theta by adjacent side, which is this value, over the hypotenuse. But hypotenuse equal to 6. So it means the 6 cancel out, because it's going to be this square root over 6 times 6. And for 3 theta, I'm going to get theta from here. Knowing, x minus 3 equal to 6 sine of theta. So it means sine of theta is equal to x minus 3 over 6. I'm going to just write it here. So from our substitution formula, so you guys can see here sine of theta is equal to x minus 3 over 6. Opposite side over the hypotenuse. Now to isolate, should be 3 here. To isolate my theta, I'm going to apply the sine inverse on both sides of this equation. It means theta is equal to sine inverse of x minus 3 over 6. And this is what I use here to substitute sine theta by its value to get this part here. Okay, so basically you guys can see here you completing the square technique, in fact, use what we did last week about, the substitution rule. Anytime you complete the square in the first step, the second step gonna be using one of the trig substitution formula that we've seen last week. Okay, because when you complete the square, you guys will get either the summation of two squares or the difference of two squares, as our first example here. And in both situations, you guys can use the trig substitution. Any question? Yeah. This? Here? Here? Okay, so it's just obtained from this substitution here. So we have x minus 3 is equal to 6 sine of theta. Okay, and now to get the value of theta, I have to the value of x. I need to isolate my x, so it means x is equal to 6 sine of theta plus 3, right? And I replace it here on the top because I have x here. I replace by its value to get exactly this numerator. Is it okay? And this is my dx. So dx here is substituted by its value. The value of dx is right here. And I just substitute by its value. All this is your dx. For the denominator, it's just coming from here. So for the denominator, you substitute here x by, that's what I did here, substitute x by the sine, 6 sine plus 3. And from the bottom here, I have the 36, I just copy it. And here x minus 3, I replace it by 6 sine of theta and you square it. Okay, so the integral is x over, after completing the square, I got this 36 minus x minus 3 squared dx. And now this is equal to integral. So you substitute here x by its value to the numerator. So it means my numerator now becomes 6 sine of theta plus 3, right? And the denominator now becomes square root of 36 minus, but this bracket x minus 3 is what we call 6 sine of theta. At the beginning is going to be 6 sine of theta, you square it. Okay, so that's why here I got 36. When you square it, it becomes a 36 sine square, coming from here, this square. And the dx is equal to 6 cosine theta d theta. Is it okay? Well, any other question?
So could you please explain the substitution for cos after doing the integral?
For cos, this? It's obtained from the right triangle here. Cosine is equal to adjacent side over the hypotenuse.
Okay. Thank you.
Is it okay?
Yes, it is.
Yeah. So and now the 6 cancel out because you have here minus 6 cosine of theta. Okay, and it's gonna be minus 6. So cosine of theta, you can get it from the right triangle, gonna be adjacent side, square root of the adjacent side over the hypotenuse, gonna be 36 minus, so bracket x minus 3, you square it. This is adjacent side over the hypotenuse. And then, you know, the 6 can cancel out here. So that's why we only have minus square root of, because we simplify the 6. Sounds good?
Yes.
All right. Any other question? All right, so let's move on to the second question. All right, second question here. Again, we integrate 1 over x squared plus 2x plus 5 to the power 3 by 2. So you guys have, again, this form. And keep in mind, to the power 3 by 2 is just square root of this bracket to the power 3. So that's why I said you have, again, this 4, the square root. Okay? So it means you can use the completing square technique. So you need first to complete the square, and when you finish it, as I told you, you will get either the summation of 2 square or the difference of 2 square always. And in both situations, you guys can use the trig substitutions. Okay. All right. So now let's see how to complete the square in this case. All right, for this example, so you have exactly this integral. And you guys can see the missing part is 1 because you have x squared plus 2x. It means, you know, x is the first term, you square it, and we have 2ab. So it means we already have 2. A is your x, so missing is just b equal to 1 in this case. So since b is equal to 1, the missing part in order to get a square is 1 square, which is equal to 1. So that's why I add here 1 and subtract 1. And I copy the last term. So we did, you know, completing the square, you know, last week by using several examples. And in this case, you know, the first 3 terms here is equal to the square. That's why we add the 1 in order to get the square. So it is exactly equal to x plus 1 squared, these 3 terms. And for the remaining terms, we have here minus 1 plus 5, and minus 1 plus 5 is equal to plus 4. So now, again, here you guys have the summation of 2 squares. It means we have this situation here. In this case, we have the situation square root of b squared x u squared plus a u squared. Okay, and in this case, what is b? B is equal to 1, and my capital X here is equal to all this bracket. X plus 1 stands for capital X, and this is my a squared. A squared equal to 4. Again, here you guys have summation of 2 squares. And for the summation of 2 squares, you guys know the substitution gonna be x, capital X. So this is my substitution, x equal to, so this is my x. We have x squared. So here x is equal to a over b tan of theta based on what we did last week. And in my example, this capital X is equal to all this. This is my capital X, the x plus 1 here. So that's why we said here, this is your capital X, as you can see. In this case, a is equal to 2 because a square is right here. This is your a square. And b is equal to 1. And capital X is equal to x plus 1. Your x plus 1 is your capital X. And you guys can see from this substitution form that we've seen last week, is going to be a, which is 2 over 1, going to be your tan of theta. And this is your capital X. Now you can calculate dx. You differentiate the right left-hand side, going to be dx only because this is a constant. So the derivative is going to be 0. And you differentiate the right-hand side, going to be 2 times. You differentiate tan is going to be secant squared theta d theta. Okay, so now we're ready to substitute. So we substitute from here. Your dx, you guys can see the dx is 2 sine theta, sine squared theta d theta. That's what I got here. All this and this d theta is your dx. Okay. So all this is dx. This is dx. As you can see it from here. And for the denominator, you substitute here. As I told you, you guys can see x plus 1 is equal to 2 tan of theta. When you substitute here and you square it, it becomes 4 tan squared theta. Okay, it becomes 4 tan squared theta plus 4 to the power 3 by 2. Is it okay? So now I'm going to take this 4 out. Okay, to take 4 out to the power 3 by 2, it becomes 8 because the 4 to the power 3 by 2 is equal to root of 4 to the power 3. Root of 4 is equal to 2. To the power 3 is going to be 8. And inside this bracket, it remains only tan squared theta plus 1. Okay, I'm just going to write down here the step that I skip going from this step to this one. So you guys can see here what I got is, so I have 4 tan squared for from the denominator, tan squared theta plus 4, and the whole thing to the power 3 by 2. I'm just going to show you how it the 8 was obtained. Okay, so I'm gonna factor out the 4 because you guys can see 4 is a common factor. So it means this is equal to 4 times tan square of theta plus 1 when you factor out the 4 to the power 3 by 2. And here I'm going to split it into exponent going to be 4 to the power 3 by 2 times tan square theta plus 1 to the power 3 by 2. Okay, and this term here is just equal to 4 to the power 1 over 2, the whole thing to the power 3, the same thing, right? And the brackets, so you guys can see tan squared theta plus 1 is exactly what I got here. And tan squared plus theta is equal to secant square, as you know. to the power 3 by 2. But you know, 4 to the power half is equal to root of 4. And root of 4 is equal to 2 to the power 3. That's why it becomes 8 here. Times. And here you guys have sine square. Sine gonna be a sine cube here. Secant cube of theta. And that's exactly what I use here to get this part. Okay, so you guys can see here how the 8 was obtained is what I explained here, because it is just root of 4 to the power 3. That's why we got 8. And the bracket tan square plus 1 to the power 3 by 2 becomes a secant cube, because tan square plus 1 is just secant square. But secant square to the power 3 by 2 is just secant to the power 6 by 2, which is equal to 3. Any question before I move to the next page? And now to get the last step here, what I did is simplify by secant square. So the numerator becomes 1 and the denominator is now secant of theta. And as you know, 1 over secant is in fact equal to cosine. It means now my integral gonna be 1 by 4 integral of cosine of theta. Any question? All right, so you can move to the next page. As I told you, you guys can see here, we substitute 1 over secant theta is equal to cosine. That's what I did on the top of the next page. It's gonna be 1 over 4 integral of cosine, because 1 over secant is equal to cosine. So we'll get cosine of theta d theta, and the integral of cosine is equal to sine theta plus the constant c. Now we have to substitute back, and to do so we use the triangle here, because we've seen at the beginning we said tan of theta equal to, at the beginning our substitution was tan of theta. Okay, so tan of theta equal to x plus 1 if you look at your substitution formula over 2. So it means if you use this triangle here, tan of theta, as you know, from the right triangle is equal to opposite side over the adjacent side. So that's why the opposite side here is my x plus 1, and the adjacent side is 2 coming from our substitution formula. And by using Pythagorean theorem, we will get this side, because the Pythagorean theorem says the hypotenuse is equal to the square of the adjacent side plus the square of the opposite side. That's what I have here under the square root. And now I'm ready to calculate sine of theta from the triangle here. So you guys know sine is equal to opposite side over the hypotenuse. That's exactly what I use here. The opposite side is x plus 1, and the hypotenuse is square root of 4 plus x plus 1 you square it. And this is my sine of theta obtained from the right triangle plus the constant c. And we're done. Any question?
So please, could you go to the previous slide for a sec?
The page here or the PowerPoint?
No, this
one?
Yeah.
Okay.
All right, thank you.
Well, are you done?
Yeah, I'm done. Thank you.
All right, so this last example, conclude the completing square technique. All right, so now the next method is what we call the partial fractions decomposition or partial fractions expansion. Okay, and this technique is used to simplify an integral, of a rational function. So that's why I'm going to start by giving you the definition of a rational function. It's just a ratio where the numerator is a polynomial function and the denominator is also a polynomial function. And that's what we mean by a rational function. It's going to be always a polynomial over a polynomial. And a polynomial function is a summation of powers of x. That's what we mean by polynomial. A summation of powers of x where its exponent is a positive integer. If you guys have an exponent which is a negative integer, you don't have a polynomial. If you have an exponent which is a fraction, it's not a polynomial. All exponents should be positive integers. Okay, and when you guys have two rational function now, a rational over a rational, that's what we mean by a polynomial over polynomial is what we mean by a rational function. And here are two examples of rational functions. The first one is here f of x equal to, as you can see, the numerator is a polynomial function. Same for the denominator. As I told you, polynomials means the summation of powers of x, and each exponent is a positive integer, as you can see here. And the highest exponent is what we call the degrees of the polynomial. So this is a degree of the polynomial. Because the highest power for the numerator is 5, it means the degree of the numerator is equal to 5. It doesn't make sense now to say the degree of f of the rational functions. The degree is related to the polynomial function, not to the rational function. Okay, so here what I said is the degree of the numerator is 5 because 5 is the highest exponent for the numerator. And for the denominator, the degree is equal to 4. Okay, so keep in mind what we mean by the degree, because this is very important key for partial fractions decomposition. And for the second example of rational function again, so we have a polynomial of degree 5 over a polynomial of degree 7. Okay, again, we have rational function. So this is what we mean by rational function. And partial fraction decomposition is a technique to simplify this kind of function in order to be able to integrate it. Okay. All right. Now let's get started with the partial fractions technique. So before applying this technique, make sure you guys have this situation satisfied, these conditions satisfied. Okay. Otherwise, it's not allowed to use the partial fractions decomposition. So basically, you guys have two conditions that need to be satisfied. The first condition is you have a rational function, is your first condition. And that's why in the previous start, I defined what we mean by a rational function. If you don't have a rational function, don't try to use partial fractions decomposition. Now, if I verify the first condition satisfied, here is the second condition in red color. The second condition says the degree of the numerator should be less than the degree of the denominator. Okay, so you have to verify that. And we know now what is the degree of a polynomial. We're supposed to get a polynomial over a polynomial. That's the first condition. And in the second condition, the degree of the numerator should be less than the degree of the denominator. Okay. Now, if the second condition is unsatisfied, you guys have to use long division in order to get it satisfied. Okay. So use the long division. So next, I'm going to show you how to use the long division. I'm just going to show you an example. So let's suppose you guys have this rational function. So you have f of x equal to a polynomial over a polynomial. So here the polynomial is 2x to the power 3 plus or minus x. This is the numerator, minus x squared plus 5x plus 2. Okay, so this is a polynomial function. The denominator is also a polynomial function equal to x, you square it plus x. So you guys notice here, the first condition is satisfied, as I mentioned here. The first condition here is you have a rational function. So we have a rational function because the numerator and the denominator are both polynomial functions. But the second condition here is unsatisfied because you guys can see the degree of the numerator is equal to 3 and the degree of the denominator is equal to 2. So that's why here we can say this is not satisfied. And as the remark says, when the second condition is unsatisfied, you guys have to use long division in order to get it satisfied. And the long division gonna be dividing the numerator by the denominator. And you divide it by just using the same process like when you divide real numbers. It's the same process, okay? So I'm gonna show you how to divide. So you guys have here the numerator, which is equal to 2x cubed minus x you squared plus 5x plus 2. And the denominator is x you squared plus x. Okay? So first step, when you guys want to divide here, make sure so you rearrange the numerator and the denominator by getting from the highest exponent to the smallest one. So you have to get that order if you want to use a long division. So you guys can see here the highest exponent is 3. After we have 2, it's decreasing. So we have again here a decreasing order. Okay. Now, otherwise you have to rearrange the whole thing if the question mixed up, the terms. Now you ask yourself, which number or which value do I have to multiply with x squared in order to get 2x cubed? Which value? What do I have to multiply with x squared to get 2x cubed?
2x.
2x, exactly. So it's going to be here 2x. And 2x times x squared going to be 2x cubed. And 2x times x here going to be 2x squared plus 2x squared. And you subtract these two lines. So when you subtract first line minus the second one, so get 2x cubed minus x cubed going to be 0. Minus x squared minus 2x squared going to be minus 3x. You square it. And you have 5x now. Here is 0. So 5x minus 0 going to be just plus 5x plus 2. And you check if you have to stop your division here. Okay. Your stop criterion gonna be when the rest here of your division has its degree less than the degree of the denominator. Okay, so it means as soon as you know the rest has its degree less than 2, you stop. So here it's not less than 2, it's equal to 2. So it means you can still do or perform the division here. Again, same question, which number do you have to multiply with x squared in order to get minus 3x squared? Is going to be, which value do I have to multiply with x squared in order to get minus 3x squared? Exactly, minus 3. So minus 3 times x squared going to be negative 3 x squared. And minus 3 here times x going to be minus 3x. And again, you subtract these two lines. Okay, so when you subtract now, so you subtract here, it's going to be minus 3x, so minus minus, it becomes a plus 3. So we'll get 0 here. So we have 5x minus minus 3x going to be 5x plus 3x going to be plus 8x. And last time we have 2 minus 0 is going to be plus 2. And you guys can see here, the degree of the rest now is less than the degree of the denominator. So we stop our division. As I told you, you stop your division as soon as the degree of the rest is less than the degree of the denominator, and that's exactly what we have. The degree of this rest is equal to 1, and the degree of the denominator is equal to 2. We stop the division. So when you stop the division, it means, when you divide, this polynomial with this 1, your solution going to be 2x minus 3. So it means this is equal to 2x minus 3, but we have the rest. The rest is not 0. So we have to add the rest. It's going to be plus now. So the rest is equal to 8x plus 2 over the denominator, x squared plus x. And this is just obtained from something that you guys already know. For example, when you divide 7 by 2, as you know, when you divide 7 by 2, you use the same process. Okay, solution going to be here 3. And 3 times 2 going to be 6 here. And you subtract 7 minus 6 to get 1. That's exactly what I use here. You subtract. And the rest is equal to 1 in this case. So it means 7 over 2 is equal to the result of your division here, which is equal to 3, plus the rest over the denominator. So it's going to be the rest is 1 over the denominator. You guys can see when you calculate the common denominator, 2 times they're going to be 6 plus 1, 7 by 2. And that's exactly what I use here. So this stands for my 7 numerator. This is the equal to 2, and it's going to be exactly the result of your division plus the rest over the denominator. That's exactly what I use here. Is it okay? Any question? Okay, so you guys have to use this if the second condition is unsatisfied. Otherwise, you don't need it. Okay, you have to do it if you realize the degree of the numerator is greater than the degree of the denominator, so you divide in order to make it satisfied. You guys can see now you have a two polynomial function, and now the degree of the numerator is 1, and it's less than the degree of the denominator. Now it's satisfied. The condition in red color here now is satisfied by the second term here. Okay, and that was the purpose of using the long division. Any question?
No, sir. That's good.
All right. And that's exactly what we got here. Oops. That's exactly what we got here. This is a long division that I already used. So this is the result of the division, and this is, the numerator is the rest over the denominator. Okay, and be careful. It's only used when you guys have the situation. The degree of the numerator is greater than the degree of the denominator, so you will not be able to apply the partial fractions decomposition. Okay, so now we're ready to see exactly what is the partial fractions decomposition, because we now know the conditions that need to be satisfied before using the partial fraction decomposition. So based on that, we'll see now the different step for the partial fractions decompositions. Okay. So let's suppose here you guys have to integrate this function. At the beginning here, I'll not show you how to use it to calculate integral, because this technique can be seen as just, a technique to simplify your function. That's it. Okay, and after that, you calculate the integral. Okay, so now we will see how to simplify the function first. All right. We have to integrate p of x over q of x, where p and q are both, polynomial functions. And we assume here the second condition is satisfied. So it means, the degree of p numerator is less than degree of q, which is the denominator. So since the two conditions are satisfied, so now we're ready to apply the technique. And what the technique says, in the first step, you guys have to factorize the denominator, the bottom. You factorize it until you get linear factors and or irreducible quadratic factors. Okay, because we can get, only linear factors or only quadratic factors or both. Okay, so that's why I said and or. So you factorize first your denominator until you get linear factors and or quadratic factors that are irreducible. So quadratic factor is irreducible if and only if we can factorize it. That's what we mean by irreducible. And you guys already know how to factorize the quadratic equation by calculating the discriminant d, b squared minus 4ac. And if it's a negative, it means it's not possible to factorize the quadratic equation. Okay. So as I said here, for example, This is what we mean by quadratic factor. It's going to be ax u squared it plus bx plus c. This is a quadratic equation. And you know, this equation here is irreducible if and only if we cannot factorize it. And if you want to know if this is it possible to factorize, so you guys know you have to calculate b squared minus 4ac. And if this is negative, it means we cannot factorize. Okay, that's what we mean by irreducible quadratic factor. And real means, you know, the coefficients are real numbers. Okay, now this is the first step. In the second step, as I told you, you guys will linear factors and irreducible quadratic factor. And from each linear factor, the linear factors are right here. Ax plus b is a linear factor to the power n, so it means it's repeated n times. For example, you can get, you know, 2x plus 3 to the power 5 is going to be 2x plus 3 times 2x plus 3 times 2x. It does repeat it, you know, 5 times. And from each linear factor, which is repeated n times, you guys will get n terms. You can see here we have first term, the second one, the third one, up to the last one, which is n term. Because here you have n, you know, as the exponent. So it means this linear factor is repeated n times, that's the meaning. And each linear factor repeated n times generates n terms. It's repeated. If it's not repeated, it only generates the first term here, if n equal to 1. And a1, a2, a3 are all constant. They are real numbers. We'll see later today or tomorrow how to find them. At the beginning, what I want you guys know to do is how to get the partial fractions decomposition. And we'll see later how to calculate the coefficients, because calculating the coefficients are much more easier. Okay. All right, a1, a2, an are constant, are real numbers. And you guys can see the different denominators. The first denominator is just, you know, a copy of the linear factor. And the second one, same thing, but you square it because it's the second term. For the third term is going to be to the power 3, up to the last term is going to be to the power n, and you stop. And all these n terms are from one linear factor. The reason why we got n is just, you know, this linear factor is repeated n times, and you repeat it for all linear factors. And now for the quadratic factors, because from step 1, I told you after getting your factorization, so you guys will get linear factors and quadratic factors. And from each linear factor, you use the second step. And from the quadratic factors, you have to use exactly the third step. So here is just, you know, one quadratic factor, and it's repeated n times. Sometimes it's not repeated. And if it's not repeated, you will get just one term. If it's repeated twice, you will get 2 terms. Three times, you will get 3 terms, and so on. So here is repeated n times. That's why we'll get n terms. And the denominator is similar to what we did for the denominator here in step 2. First term gonna be a copy of, you know, your quadratic factor. For the second term, the same copy, but you square it because it's the second term. For the third one, you write it to the power 3, and so on up to the last one. Okay. Now, when we want to get the partial fraction decomposition, we have to add all terms obtained from step 2 and step 3. And you will get our partial fractions decomposition. Okay, so next I'm going to give you an easy example, and we'll see exactly what we mean by step 2 and step 3. Okay, and this step is repeated for each linear factor, and this is for each quadratic factor. And now if you add all these terms, as I mentioned in the last step here, so if you add all these terms obtained from step 2 and 3, so you'll get your partial fractions decomposition. Okay, and you guys can see here in step 1, 2, 3, and 4, we didn't use the numerator. We only use the denominator. Okay, so numerator will be used later when comes time to calculate all these coefficients. A1, A2, A3 are constant. Similar for these values, B1, C1, B2, C2, and so on are all real numbers and they are constant. So we'll see later how to find them. And here I just use letters with index 1, 2, 3. You guys can use whatever you want. Okay, you can use A1, A2, or you can use A, B, C, D. It's up to you, doesn't matter. It's just a constant, and at the end of the day, we'll get the same value. Okay, so we'll see later how to find them. All right, I'm just gonna give you quickly one example, and you guys can see how to deal with the step 1, 2, and 3. All right, let's suppose here you guys have x squared plus 3x plus 5, for example. And this is your px, the numerator. Okay, and denominator. So these two functions always exist. You have a polynomial over a polynomial. This is the first condition before applying the partial fraction decomposition. As I told you, first condition, you're supposed to get a polynomial over a polynomial function. Let's suppose here the denominator is already factorized. Okay, so we have, for example, let's say x minus 1 as a first linear factor, and then we have x plus 3, for example, is my second linear factor, and it's repeated twice, and I have a quadratic factor which is equal to x squared plus 2x minus 7. I'm going to plus 7 and e squared. So this is repeated twice. Okay, I'm going to change it here. I'm just going to make repeat it 3 times. Okay, we suppose here the first step is already obtained. So the first step says, as I told you, you factorize the denominator q of x until you get linear factors and quadratic factors that are irreducible. So here you guys can see we have the first is a linear factor, the second factor is a linear factor, and it's repeated 3 times. The last factor is a quadratic factor because the degree is equal to 2. That's what I mean by quadratic factor and quadratic equation, and it's repeated twice. And again, it's irreducible. As I told you, if you guys calculate b squared minus 4ac is going to be negative. That's why this part is irreducible. Okay, so you calculate here b squared minus 4ac as I told you. So you've seen this formula in high school. In my example, b equal to 2, so we'll get 2 squared minus 4ac. 4 times a is equal to 1 is the coefficient of x squared, and c equal to 7. And this is negative. So that's why we can conclude we cannot factorize. So it means in this case, it's not irreducible. Okay, So anytime you guys have quadratic equation and want to know if it's reducible or not, you calculate this, b squared minus 4ac. If it's a negative, it means there is no solution, you cannot factorize it. Now, the condition is satisfied. We can go to the second step. And what the second step says is, okay, so from the second step, you guys can see here, from step 2 in green color, from each linear factor repeated n times, you can get n term having this form from each of them. Okay, so here we have two. So here we have two terms, two linear factors. So it means from the first linear factor. So for example, from the first linear factor, from this one, since it's not repeated, I'll get just one term because it's not repeated. And the term gonna be, I'm gonna call it A0 or A1, doesn't matter how you name it. Okay, A1 over x minus 1, one term only. And from the second one, the second linear factor, in this case, it's repeated 3 times. So it means it generates 3 terms. And the first term gonna be, so since I already use A1, I cannot call it A1. I'm gonna change the name. I'm gonna use A2 over x plus 3, okay? It generates 2 terms. The next one gonna be A3 over x plus 3, you square it. This is, what the second step says. For the second step, from each linear factor, you guys will get some terms. So here this linear factor is not repeated. That's why we got one term. So this linear factor is repeated 3 times. Is gonna give us 3 terms. We're gonna get here A4, for example. Okay, doesn't matter if I use A1, A2, A3, or 4. I can use A, B, C, D. Okay, it's up to you. You don't have to worry about how we name our variables. You can use any letter. Okay, and the denominator is x plus 3 to the power 3. You stop because here it's repeated only 3 times. You cannot add to the power 4. You stop here at power 3 because it is repeated 3 times. Now from the last linear quadratic factor here, so since the quadratic factor is repeated twice, it means it generates only 2 terms. And for this term, you guys will get B1 x. You guys can see here the numerator for the quadratic factors is different to the numerators for the linear factors. So here for the linear factors, the numerator is always a constant. And for the quadratic factor is going to be a linear equation, B1x plus C1. This is exactly what the third step says. Over, you copy this, is going to be x, you square it, plus 2x plus 7. Okay, not done. So because here it's repeated twice, that's why we have 2 terms. Going to be now plus, oops. So it's going to be plus here, B2, so B2x plus C2 to the over so we'll get here x squared plus 2x plus 7 plus 2x, oops, plus 7, and you square it. because you have two terms, is repeated twice. And the last step says, you guys can see all these terms are obtained from step 2. So this term is obtained from step 3. And for step 4, what step 4 says is you have to add all terms obtained from step 2 and 3. So this is from step 2 plus from step 3. And all this is what we call the partial fractions decomposition here. This summation. So this is what we call the partial fractions. As you can see here, we didn't calculate any integral, okay? So that's why I said at the beginning, partial fraction, in fact, is not a technique to calculate the integral. It's just a technique to simplify the function that you want to integrate, if your function is a rational function. So that's why I started here by showing you how to get the partial fraction decomposition, and later we'll see how to apply it in the case of integral, if you want to calculate the integral. And just keep in mind, at this step, I did not calculate the coefficients A1, A2, A3, A4, B1, C1, B2, C2. We'll see later how to find them, okay? At this step, what I want you guys know is how to get the partial fraction decomposition. So later we'll see how to get the coefficients and calculate integral. Any question? Any question?
No, sir.
Okay. Can I erase it? All right, let's see some examples. Okay, as you can see from this example 7, what we want to do is just to get the partial fraction decomposition without calculating the coefficients. The coefficients are, you know, what I call A, B, C, A1, A2, and so on. Just the letters. Okay, so we'll see later how to find them. But at this step, what I want you guys know is just to get the partial fraction. That's it. And later we'll see how to use it to calculate integral. So first example, we have 1 over x cubed plus 1. First of all, we verify if the two conditions are satisfied. So 1 is a polynomial because 1 is equal to x to the power 0. It's a polynomial of degree 0. And this is also a polynomial of degree 3. So since you have polynomial function over a polynomial function, it means the first condition is satisfied. And the second condition is also satisfied because this is a polynomial of degree 0. It's less than the denominator, which is a polynomial of degree 3. So it means you don't need to do any long division. So we have just to apply directly the method because the two conditions are satisfied. All right, here it is. And the first step says you start by calculating or factorizing the denominator. In my example, denominator is equal to x squared plus 1. And when you factorize it, so you get x plus 1 times x squared minus x plus 1. So this is the first factor, which is a linear factor. And the second factor is a quadratic factor. You guys can see the highest power is 2. That's what we mean with quadratic. And it's not possible to factorize it. As I told you how to know it, you calculate your b squared minus 4ac. So here b equal to -1, you square it, becomes 1 minus 4, which is negative, not possible to factorize. It means it's irreducible. Now, since it's reducible, we're gonna go to the second step. And the second step says from its linear factor, you can generate some terms. So the linear factor is not repeated because it is power 1. That's why it's gonna generate just one term. So since it's linear, the term generates by this factor is right here because it's gonna be just the copy. We copy this as a denominator, and the top is always a constant. This is what I called previously in the previous example A1. So here I don't want to use the index, okay? Because we don't have too much letters, so it's going to be enough to say just A, B, C, or we can use A1, A2, A3 if you want, or A1, B1, C1. Doesn't matter how you name your coefficients A, B, C. Okay? All right. And from the second factor here, which is quadratic, is going to be the same denominator, but the top going to be bx plus c. So back to our slide here. That's what I explained here. If you have a linear factor, you guys have this kind of term from each linear factor. So in our example, we only have one linear factor and it's not repeated. So that's why you only get one term. And I just call it A instead of A1, but doesn't matter, okay? It's just a name. And from the quadratic factor, in my example, we only have one quadratic factor, n equal to 1. That's why we got only one term. And I use bx plus c instead of b1 c1. But this is not a problem. You name your question by using any letter. You can use mx plus n or ix plus j or kx plus l. Doesn't matter. Okay. And that's exactly what I use here from the second. And to conclude, we have to add the 2. So this is obtained from the first factor. This term is obtained from the second factor. Now adding all terms obtained from step 1, so from step 2 and 3, you will get your partial fractions decomposition. And this is the partial fraction decomposition of this rational function. Is it okay? Any question?
No, sir.
All right. Example number 2. All right, so example number 2. So we have x squared plus 2x plus 3. Again, this is a polynomial function. Denominator is also a polynomial function. So it means we have polynomial over polynomial. First condition is satisfied. It's a rational function. Now, degree of the numerator is equal to 2. Okay. So the degree of the numerator is equal to 2, and the degree of the dem equal to 3. So it means the second condition is also satisfied because the degree of the numerator is less than the degree of the denominator. So now it means you can apply the technique without doing any long division. Oh, okay, let's see how to do it. All right. This one. Okay. So here is our second example. First step, you focus on the denominator and you factorize it. All right. So, but here I realize, from the first and the second term, x squared is a common factor from the first and the second step. So that's why I just took out, the x squared, you factor out here. So it remains only 3x minus 1. If you put it back, it becomes a 3x cubed, exactly what is here. And x squared minus 1 going to be minus x squared. And from these two terms, I'm going to take minus 1 out. That's why I got here minus 3x minus 1. If you put it back, it is going to be minus 3x minus 1 going to be plus 1. And from this line, you guys can see 3x minus 1 is a common factor. So we can take it out. So when you do so, from the second term, the first term, it remains only x squared. And here the second term becomes 1. And this is a linear factor. So good. And this is a quadratic factor. But the step 2 says the quadratic factor should be irreducible. Step 1. But this is not irreducible because this is a difference of 2 squared. It means we can factorize it. And that's exactly what we did. This is just has a form a squared minus b squared. And as you know, it's going to be a minus b times a plus b. So in this case, we only have 3 linear factors and there is no quadratic factor in this case. And step 2 says from each linear factor, repeated n times, you will get n terms. So here it's repeated just once, each of them. So it means each of them gonna generate only 1 term because they are not repeated. So from the first one, so you guys will get a because it's linear. As I told you, numerator should be always a constant. So this is what I call, previously a1, and this is what I call a2, a3. Okay. And I decided just to name them A, B, C, D. I can use any letter, doesn't matter. I can use small a, B, C, or I can use alpha, beta, gamma. You can use, whatever you want, any letter. And from the second factor, again, I'll get, this second term. It's not repeated. That's why I have only 1 term. And same for the third. And then you're done. So this is the partial fractions decomposed. Again, we're not calculating any integral. So we'll see later or tomorrow how to calculate the integral. At this step, what the question says is, I'm testing if you guys know how to get the partial fractions decomposition. That's it. Okay, so we need to practice a lot with this kind of question, and then later we'll see how to apply this technique in order to get to calculate the integral. Is it okay? Any question? All right, if there is no question, I'm gonna go to the last example, number 3. All right, for example 3, we have x over x to the power 4 plus 7x squared plus 6. Again, the two conditions are satisfied because the numerator is a polynomial function of degree 1. It's just x to the power 1. And the denominator is a polynomial function of degree 4. So since we have polynomial over polynomial, and the degree of numerator 1 is less than the degree of denominator, which is equal to 4, it means the two conditions are satisfied. So we don't need to do any long divisions in this case. So we can start by factorizing the denominator. That's exactly what the first step says. All right, so again, we're gonna take the denominator here, factorize it. Okay, so what I did here is just, I split the second term here into x squared plus 6x squared. So when you add them, it becomes the 7x squared. Okay, and from the first and the second term, you guys can see x squared is a common factor. That's why I factorize it here. And then I'll get x squared plus 1. When you put it back, it's going to be x to the power 4 plus x squared. And from the third and the last term, the fourth one, I'm going to take 6 out because it's a common factor. And I'll get 6 times x squared plus 1. And you guys can see these two brackets are exact the same thing. So it means it's a common factor. When you take it out, so the remaining terms from here are going to be x squared, and here we'll get x squared plus 6. And so we got here two quadratic factors. In this case, you don't have any linear factor. But since you have two quadratic factors and both of them are irreducible, you guys can see them. It's not possible to reduce it. You can calculate b squared minus 4ac if you want. It's not possible to factorize. Okay, so since the quadratic factors are irreducible and we don't have any linear factor, so it means we can find now the partial fractions decomposition. So from the first quadratic factor, as you can see, this is what I called previously b1 x c1. So here I change the name into b, a, and b only. What is it again? All right. Okay, so there is no here. Let's remove it. So that's what it is here. From this one, I have ax plus b. Okay, so that's what the third step is going to be. If you look at the third step here, we have this back to our. So we have this situation here, but none of them is repeated. That's why we'll get just one term, because n equal to 1 in my example. So that's why we'll get b1 x c1. But instead of using b1 c1, I just call them a x for b1. I call it a, and this I call it b. But doesn't matter how you name it. That's what I told you. Because at the end of the day, we're gonna find their values. Okay. All right, so that's exactly what we did here. It's going to be ax plus b for the numerator. For this numerator, is going to be cx plus d. I can also use b1x plus c1, b2x plus c2 if I want, but doesn't matter. Okay, it's the same thing. Any question?
No, sir.
All right. All right, to make sure you guys understand, how to get the partial fraction decomposes, I'm gonna give you one question, coming from past midterm, I guess, past final exam, I guess. Okay, and you guys can get find the partial fractions, and later we'll see how to apply it in order to calculate the integral. Okay, here it is. It's just final exam of fall 2017. All right, you guys have here your rational functions, and the two conditions are satisfied because this is degree 3. When you expand this part, it's going to be for sure more than degree 3. Okay, so as the question mentioned, you only need to find the partial fractions decomposition or expansion is the same thing without calculating any of the coefficients. Don't try to find the coefficients, we don't need it. So you name your coefficient by using any alphabetic letter. Okay, you can use A, B, C, or A1, A2, A3. It's up to you. Doesn't matter. Okay, I'm gonna give you 1 minute, to find the partial fractions decomposition by following, all steps from step 1 to step 4. So you guys are done?
Yes,
No,
Professor.
Pardon?
No, sir.
Not yet? So don't try to calculate the coefficients. You just write the partial fraction decomposition, that's it. All right, so let's solve it because we have just 8 more minutes before the end of the class. Okay, I said here my numerator is this copy x and my denominator is q of x. It's almost factorized, but the first step says you factorize it until you get linear factors and quadratic factors. So here is a linear factor, I just copy it. The second one is also linear factor is repeated twice, that's okay. But the third factor is not linear and it's not quadratic because the highest exponent of x is not 2, it's a 3. So that's why it's a cubic function. So for cubic function, we need to factorize it again. I'm going to take it from here. It's not quadratic. I'm going to take x out. So I'll get here x times x you square it plus 6x plus 8. And I'm just going to copy now the last part here, going to be just x squared plus 2 to the power 2. So the last factor is quadratic factor, and it's irreducible because it's not possible to factorize this one. Now I still have, a quadratic factor here, which is reducible because you guys can see this, we can factorize it, okay? So now we'll get here, we'll copy the last linear factor, the first linear factor here. Second linear factor and repeat it twice. So it means gonna generate, two factors, two terms. And we have x. Now I'm gonna factorize, this bracket is gonna be x plus 2 times x plus 4 times x squared plus 2. So now you guys can see now we have linear factors, except the last one. The last one is quadratic factor, but it's irreducible. So now we're ready to get the partial fractions decomposition. So we can conclude now because we're done with the first step. The first step says you have to factorize the denominator until you get linear factors and irreducible quadratic factors, and that's exactly what we got here. And from the first linear factor, now I'm going to write here px over qx to give you, the partial fractions decomposition of this rational function. All right, from the first sphere, the first linear factor, so since it's a linear, the numerator is going to be just the same thing. And since it's a linear, the top going to be a constant. I'm going to call it A. I can call it A1 if I want to. Okay. Plus now, from the second linear factor here, so this linear factor is repeated twice. So it means it generates two terms. I'm going to call the first term, B over x plus 1. Plus this one, I'm going to call it C over x plus 1 u squared. So instead of using A, B, C as I did, okay, even if you guys use A1, A2, A3, that's okay too. Okay. So this term is from here. So this one provides these two terms because it's repeated twice. And from plus now, from this term, it's just linear factor again. I'm gonna use just, and it's not repeated. It's gonna be dx obtained from this guy here. And from these two linear factors, so none of them is repeated. So from x plus 2, so we'll get just e over x plus 2 plus f over x plus 4 because it's not repeated. Plus now, so this quadratic factor is repeated, and for quadratic factor, so you'll get two terms because it's repeated twice, and the denominator first term is just the quadratic factor. Oops. So we have here x squared plus 2. And here's going to be x squared plus 2, you square it because it's repeated twice. It's exactly the same thing that I did for linear factor. So here we have quadratic factor to the power 2. And the numerator here going to be bx plus c. But since I already used b and c, I have to change the name of the coefficients. I'm going to use g x plus h and I'm going to use ix plus j, and you're done. So in this case, all these letters, alphabetic letters from A to J are constant. So we'll see tomorrow how to find them. But here the question was just to get the partial fractions decomposition without calculating any of these coefficients. That's why we stop, here. And as you can see here, how many terms you guys can check, the number of factors. So here we have 2 factors is repeated twice, 2, 3, 4, 5, plus these 2, going to be 7, 8. If you check the number of terms, it's going to be 8 too. So 1, 2, 3, 4, 5, 6, 7, 8. Any question before I let you go?
Sir,
Yeah.
what condition are we using, like gx plus h?
So we're using this one. In the PowerPoint slide, I use B1x. Remember, plus C1. Okay, over the AX plus B, AX squared plus BX plus C. Because when the denominator is a quadratic equation, that's exactly what I have, is quadratic. But in this case, you know, the quadratic equation, the B is 0, but it's not a big deal. As soon as you know the highest power of X is 2, it's a quadratic. Okay. So these two step ups. So the last two steps are obtained here is H. So the last two steps are just application of step 3. It's right here. But instead of using letters B1, C1, I just use J and H. And as I told at the beginning, this does not depend on the name of your coefficients. So you can use any letter that you guys want. Instead of using A, B, C, I can use A1, A2, A3, A4, A5, A6, A7, A9 here, A10, and A11. Doesn't matter. Or I can use A1, A2, A3, A4, A5, A6, and here I just use B1, C1, B2, C2. Is it okay? All right. Hello.
Yeah.
Yes.
Yeah. Yeah, I want to take it. That's what I told you. I was just answering to the question. I said that's all for today. I'm going to take the attendance before letting you go. Are you done with this?
Yes, sir.
All right. Tomorrow we'll see, you know, your mic, please. So tomorrow we'll see, you know, how to find the coefficients and then calculate integral. All right. So before letting you go, I just want to take the attendance. All right. Magamet, are you still here? Oh, yeah, I saw you. Okay. Fatima,
Here, sir.
thank you. Al-Amin,
I'm here, Professor.
thank you. Tianki Bao,
Yes, sir. I'm here.